Okay, cool. Okay, thank you all for being here. Sorry, it has been a really busy week for me, and I'm traveling next Monday, so I'm delivering this class online. Actually, uh, maybe 2, 3 times. I believe it's at least 3 times this semester. I have to deliver the class like this online, but well, with Zoom, this has been much easier than before. During the pandemic, we did all the classes like this. But of course, there is a missing in-person interaction component, but you can always find me in my office hour, or if you want to schedule a meeting with me, we can meet at any other time. So last class, we talked about some user-chosen secret for password for authentication. Everyone is still using text-based password. And we also talked about picture gesture authentication, which was an authentication with Microsoft Windows. I'm not sure if Windows still has this feature because personally, I published a paper to attack it 10 years ago. I don't know if it is still there. So like we discussed, entity authentication basically can be divided into 3 types. The first one is users and the authenticator or the verifier. They knows a secret, they share a secret, like a password, like a PIN, secret key, mother's maiden name, some shared secret, or user possesses a token. Some simple token are kind of just like a certificate. They have some information there, but do not really have any computing resources. But other tokens, they can compute. The third one is users has a physical attribute. Usually those are called the biometrics. So we will talk about biometrics next class, and we will compare all those authentication approaches. So today we mainly talk about the second one. A user processes some kind of token, especially when the token has some computation power. So going back to the text password example. So imagine we use text password for remote authentication, so for online authentication, not only for local authentication. So local authentication means you just trying to access your phone, access your computer. There is a direct physical access. So remote authentication means there is a computer network between the verifier and the user. So previously, we have those kind of we use password for those kind of remote authentication. But the problem is the password has to be sent as plain text in the network. So anyone on the network will be able to eavesdrop the password. So not only the password, some other sensitive secret can also be observed. So let's say maybe 15 years ago or 13 years ago, no, almost like 15 years ago. SSL or TLS has not been widely deployed. So when you visit the website, you're not really using HTTPS. You're just using plain text HTTP. So you log in your Gmail account. That time Gmail was already very popular. You log in your Gmail account, you will type your password. Then your password will go from your browser to the Gmail server in plain text. So anyone in the middle will be able to say your password. Someone in the same Wi-Fi network as you will be able to say the password. So after you type your password, the correct password, the Gmail server authenticates you. Gmail will use a cookie to identify this communication. So Gmail server will send you a cookie. Then later, every HTTP request you send to the Gmail server, you have to include that cookie. And that cookie is randomly generated for every login. However, that cookie is like a certificate or token Gmail gave you that you can use that to access your Gmail account. So anyone on the website, on your network, even if they do not get your original password, but they didn't capture the very first package, they capture every other package between your browser and the Gmail server can also get the cookie. As long as they can steer that specific cookie item, then they can still access your Gmail account. Okay, that's because the communication is just a plain text. So after HTTPS, this problem has been solved. We do not really send plain text anymore. So also other old services like Telnet, they just send everything in plain text, including password. So one of the idea to address the limitations of text-based password is, how about every time we authenticate ourselves to a remote server, we use a different password. So every password we use, we will only use it once. We always change it, right? So the idea is called a one-time passwords, okay? So there are many ways to implement this. First of all, let's say the user and the remote system can agree on a list of passwords. Somehow we agree with the Gmail server. This is a list of passwords. Every time I will use a new password, I will never reuse my old password, right? That's one way. But obviously, this approach is very difficult to implement. The idea seems good, but very difficult to implement. How do you share unlimited number of passwords there, right? Very difficult. Another way is the user and system will update the password after each successful login. Maybe the user will send a new password encrypted, which is derived from the current password. However, those approaches not also a good idea. First of all, it also brings some burden to the users. They have to generate a new password every time and somehow send the password to the server. So back in 1984, Leslie Lamport, he coined the term one-time passwords, and he designed a system to achieve one-time password. It's not a perfect system. It's just an idea. He published a paper called Password Authentication with Insecure Communication. So this is a very interesting idea using hash chains. That's why we will take a look at it. It's not really practical. No one is really using it, but some variants from this protocol has been used in some production systems, a little bit different. So Leslie Lamport actually got his Turing Award, but obviously not for this paper, for his other contributions to the theory of distributed and concurrent system. I believe he also developed one of the he also made some contributions to formal methods. I use one of the tools called linear temporal logic verification. I believe he developed that back in the 80s or maybe even earlier. So let's take a look at how this, in his original paper, how this one-time passwords work and why this is not really an ideal solution. Okay, so the idea is a new password is derived with each instance of the authentication protocol using a one-way function. So he actually named the system S/key, but it doesn't really matter. Yeah, the name doesn't really matter. Okay, so the protocol works this way. The user first selects a random number, a secret. Let's call that secret K. Then the user will generate a sequence of values by hashing that secret, and hash it once, hash it twice, and hash it t times. Okay, so the user first have a K, hash it once, get a HK, then hash it twice, get HHK, and we can hash that t times. Then the user has to somehow securely give the last one, so the HTK to the server, but nothing else. The user is not going to give the server K, HK, HHK, but only the last one in that. So this one is actually a hash chain, right? So give the last one in the hash chain to the server. So we know that here we assume that the hash function cannot be reversed. This is a secure hash function, which means even if the server gets the HTK, the server cannot get the HT minus 1K or HHK or HK or K. The server will not be able to do that, right? The password for each authentication is actually the previous item in the original hash chain. For example, if this is the user already gave HTK to the server, so the first time the user wants to authenticate him or herself, the user will use HT minus 1K. So what the server has? The server has HTK, and the user gave the server HT minus 1K. Then what the server does? Server will hash what the user gives the server, which is HT minus 1K, and the result of the hash will be HTK. So the server will compare if what the server stores, the HTK matches when it hashes what the user gives. Okay, all right? Does that make sense? So if that matches, then the server believes the user is legit because no one should be able to calculate T minus 1K. So the second time, then the server will store that HT minus 1K there. So the second time the user authenticate, the user will send HT minus 2K there. Okay. So this is how the system works. Let's have a more concrete example. Let's say we have, so the one of the limitation here is before all the authentications, we need to decide the number T, which obviously is not practical. You have to say for the next 10 times of authentication, I'm going to use this approach, or next 20 times of authentication, I'm going to use this approach. Okay, so let's say T is 5. So user chooses K and compute HK, HHK, or H3K, H4K, H5K. Then the user gives H5K to the verifier. So during the first authentication, the session 1, what we have is user will give H4K to the verifier. Verifier hashes that to check if it equals to H5K. So or any other attackers, they will not be able to get H4K. So let's say they have just a random number, and they send that random number to the verifier. You just do a simple brute force guess. Then the verifier will hash that random number, and they will find out the hash result doesn't match H5K. Then we will deny that authentication request. Okay, so that's how simple it is. Like I said, this is not a perfect solution. You can say that in theory, this looks like a very beautiful solution, but in practice, it's not really usable. You need to first determine key. You also need to assume the hash function is secure, right? So an even stronger form of authentication, which is the foundation for many authentication protocols we are using today, is where the user doesn't have to send any secret to the verifier. In the previous one, we're still sending a password to the verifier. So a most stronger one, we don't send any secret. So what the users does is to convince the verifier without leaking information about the secret. And usually, the basic structure of such a protocol is what we call a challenge response protocol. So the verifier usually will send a challenge to the user. And the user has to use the challenge and the secret to compute some response and send back to the verifier. Without having that secret, the attacker cannot generate a legit response. Okay, but the secret is never disclosed. The last secret is never transmitted through unsecure channel. So this challenge response paradigm is the foundation for a lot of the protocols we are authentication protocols we are using today. And there are many challenge response protocols we can build using different crypto primitives. Even using Mac, we can do that. So we're going to look at several examples. Let's say, in this case, we are not talking about authentication between a user and a server, but just two users, Alice and Bob. Alice is authenticating to Bob. So Bob wants to verify Alice's identity. So Alice has a secret S, and Bob has a verification value V. Let's say Bob sent Alice a challenge. The challenge sometimes it's just a random number, or we call it a nonce in crypto protocols, which is number used once. So nonce. Then Bob sent Alice the challenge number C, and Alice will compute a response, which is a function of the secret and that challenge. Then send it to Bob. Then Bob will verify that challenge R verify the response R using the challenge and another verification value. So the verification value here may be just somehow related to Alice's secret. Yeah, you can say this could be something like a public key and the public key crypto, right? But doesn't have to. Of course, even a challenge response protocol may have many vulnerabilities. They can be attacked. So next, we are going to look at some concrete examples. Before that, let me say that many token-based authentications, they follow this challenge response paradigm. The old storage-only tokens may not have this. For example, your credit card, if you are just swiping your credit card using the magnetic part, they do not have a challenge response. Basically, the magnetic part has your secret. When you swipe it, it reads the card reader reads those secret. Okay. So obviously, some of those approaches we combine with a password, a PIN number to make it safer. Then there are more advanced tokens, smart card based. So smart card is just a small computer. It has its own CPU. It has its own storage. It's a microprocessor or a micro controller. And so several years ago, all US-based credit card we have been changed to smart card based, right? So you can see there is a little chip there. The little chip is called smart card. Also, our same card we used in our phones. They are just a special smart card. They are also smart card issued by those carriers. Okay. So the reason we are switching to smart card based or chip based credit card is because we're performing some challenge response. When you insert your card to your card reader, the card reader is going to send some challenge number to a card. The card is going to perform some calculation and send it back to the card reader. Obviously, the card you get is either issued by bank, government, or let's say some other entities. They like telecommunication carriers. They embed some secrets in the smart card, and smart card can do computations. I personally designed those systems when I was doing master's degree actually. So I was programming smart card when I did my master degrees. Yeah. So let's say also the other thing like a USB dongle, they are almost the same. Okay, so the USB dongle, the USB part is just how the device connect with your computer or other devices. The dongle itself may have a microcontroller and or maybe my microprocessor. Okay, so let's say how a very simple challenge response protocol works and why it is not secure, for example. Let's say, going back to our previous example, Alice and Bob. Alice wants to authenticate to Bob. Bob wants to verify Alice's identity. Let's assume Alice and Bob, in this case, they already share some secret key, like AES key. Somehow they already share AES key. In the smart card example, you can say this can be easily achieved. When your bank issues the card, your chip card to you, you can embed AES key there, and only the bank and the card knows the AES key, right? So when Alice wants to authenticate to Bob, Alice will first send a message to Bob saying, "Hey, Bob, I'm Alice. I want to be verified." Then Bob will just generate a random number. The random number here is I use R here. The here means random number, and this random number is a challenge. Then when Alice gets this challenge, what Alice does is to use like AES to encrypt this random number using the key shared between Alice and Bob. No one else have this key, so no one else will be able to encrypt this random number correctly, right? So when Bob gets this random number, when Bob receives the plain text, the ciphertext, then Bob will just decrypt this ciphertext using the shared key. And to say if the decrypted message is the same as the random number he sent before. If they match, it means Alice really have this AES key. But the secret here is the AES key was never disclosed to anyone on the network. So this is a very simple authentication. Okay, there are many bugs of this one, but this is the fundamental paradigm of challenge response. Of course, we can change the protocol a little bit, and there may be some benefit of doing that. When Alice, or maybe they are the same. So let's say Alice tell Bob, "I'm Alice." Then Bob will not send the challenge. Instead, the Bob will encrypt the challenge using the key and send it to Alice. And Alice has to decrypt that and send it back to Bob to show that I am able to decrypt this message. So I have the key. So very similar idea. We can do similar things using the public key protocols. Here, let's say the first one, we assume Bob has Alice's public key. So Alice send a message to Bob. I'm Alice. Bob send Alice a random number. Then Alice will just sign that random number. So when I say sign here, means Alice will use her private key to encrypt this random number, right? Then when Bob got that number, then Bob will using Alice's public key to decrypt this. If it matches, then Bob knows only Alice has a private key. Only Alice should be able to sign that random number. Or another approach is Alice can so the same thing. So instead of directly sending a random number, the challenge, Bob will use Alice's public key to encrypt that random number. So Alice, who has the private key, will decrypt that random number and get the plain text of random number and send that to Bob. So Bob can verify if that's the correct number. Okay, so similar. So those two slides, we're using symmetric key crypto system and the asymmetric crypto system to build almost the same protocol. So you may think those are very, very simple protocols, right? It looks like they are not going to be used in real world. Actually, in real world, we use something very, very similar, at least years ago. So 2G, so maybe 10 years ago, there are still some 2G mobile communication system we were using. In 2G, the authentication works this way. So there are several entities. First, you have your phone. Your phone are from many different manufacturers, different companies, right? And what really binds you with your carrier is a SIM card, which is a smart card. You insert your smart card into your phone. We're still doing it, even though now we have a eSIM card. But most phones are still using a physical SIM card, and you get your physical SIM card from the carrier. So when the carrier gives you the SIM card, it embeds some keys in that SIM card. The carrier knows the keys, the SIM card knows the key, and the carrier has some entity, a simplified version. Let's say the entity is called AUC, like Authentication Center or whatever. Okay, so that's an entity which is a trusted part in the carrier's network. Then we have many base stations. There are many base stations out there. Your phone can only directly talk with the base station. Your base station will talk with the authentication server. So every time you enter a new base station or you reboot your phone, what happens is the phone will send out a message to the base station to do authentication. The purpose of this is obviously the carriers will not give you free service. You have to be their customers to get their service. So the phone will send its IMSI number, which is International Mobile Subscriber Identifier, something like that. So that could be a number, IMSI number, maybe a number in the same card, I believe. Let's say that's a number that the carrier identifies the customer. Okay, send this number to the base station. The base station will forward this number to the authentication server. Then the authentication server will generate a random number, let's say R here. Then this random number R will go through encryption function. That encryption function is called A3. So that A3 is a standard function in 2G network. There are several other functions. Another one of them is called A8. I believe there are several others. They are just the same, kind of like a symmetric key encryption algorithms. So 2G network, they were not using AES. They have their own crypto algorithms. A3 is one of them. So it will use A3 and the key shared between the SIM card and the server to encrypt that random number. And we call this result called S response, okay? Then the server will send R S response and another key to the base station. So the key name C is actually calculated using another algorithm called A8, using the key shared between the SIM card and server and that same random number. And this K3 will serve as the asymmetric encryption key between the SIM card, between the phone and the base station later, okay? So after base station receives R, S res, and KC, it will only forward the random number to the phone, okay? So when the phone gets the random number R, the phone will actually give the random number to the SIM card. Because the phone doesn't have the secret, the phone cannot calculate that. The SIM card will do the same calculation here. Because the SIM card has the key, it will use the algorithm A3 and algorithm A8 to compute two things. One is S response, one is K3. Then the SIM card will give those numbers back to the phone. Maybe I'm not sure if the KC will go back to the phone. Depends on how you use that key to do encryption. Anyway, that SRES, here I use a different color to represent that this is the one computed on the same card. The SRES, the phone will forward the blue SRES to the base station. Then the base station will just compare the SRES from the same card and the SRES from the carrier's server. If they match, it means the SIM card has the key. Otherwise, the SIM card doesn't have the key, right? So this is a simple authentication. And if they match, then the base station will just use K3 to do encrypted communication with the phone. Okay, so this is how the 2G communication communication authentication works. 3G, 4G, it's much more complicated, but the basic idea is still challenge response. We will talk about it later. So what's the problem of this protocol? There are many problems in this protocol. First of all, even the crypto algorithms, the 3G, the 2G community developed was not secure. There are bugs in the algorithm itself. So let's say one of the problem is the authentication we have here, including the authentication we have for in those two slides. This is just a one-way authentication. Only Bob is authenticating Alice. Alice never authenticating Bob. That's one of the problems in those two protocols. So going back here, the problem is we can easily introduce some fake base stations. So when a phone sent my IMSI number to a fake base station, the fake base station will just send a random number R. Behind this fake base station, there is no the legit authentication server. There is no legit carrier. And the phone will use that key to compute that S response and send to the fake base station. But the base station doesn't have the key. It cannot verify SR, and it doesn't want to verify. Okay, it just simply ignore that. The problem is the A8 algorithm. People find a box there. The A8 algorithm was not secure. The fake station will be able to find the E3, EC, even without the original key. There is a bug in the algorithm. So you can see that then the fake base station can easily build a secure communication with the phone. The phone believes it is really talking with its legit carrier. It never verify that. However, it actually was connected to a fake base station. So this has been a big problem 10 years ago. So back in 2013, you can easily purchase some underground from underground marketplaces. You can easily purchase some fake base stations like this. You can put them in your backpack. There are cyber criminals put them in a backpack and just to go to places like crowded places, packed places, to collect to people's phones and send out fake and spoofed short messages. They can pretend they are sending messages from carriers. Then in that messages, there could be, they can conduct other cyber crimes with phishing links, with other many different things. This is a very real thing. I think I personally also got some faked short messages that time. Also, this is a picture back in 2014 August. So in that month, so there's maybe a agency. They got a lot of report for fake mobile stations, and at least 19 fake mobile base stations were discovered in that month. But you can see that this is a very cheap device. So there are maybe many more fake base stations that time. So imagine you cyber criminals, they invest $1,500, then they can just go to places like Times Square. They can spoof thousands of people, tens of thousands of people in a very short time, right? That's for cyber criminals. That's 1,500 investment is not much compared to what they could get. Okay, so you can see the problem. One of the problem here is the authentication is not a mutual authentication. The phone authenticate to the server, the base station, but the base station never authenticate itself to the phone. So one way to solve that problem in 3G, 4G network, then we bring the mutual authentication. So the phone authenticate to the base station also need to prove it's a legit base station. So let's go back to the simple protocol. Let's say how we can change the simple protocol a little bit to make it to support mutual authentication. Let's say we use we use a shared secret system. So when Alice authenticates to Bob, Alice do not only tell Bob, I want to be authenticated, Alice will also generate a random number, R2. Let's say R2. Then Bob will get this message. Bob generates another random number, R1, and also uses a shared key to encrypt R2. So when Alice gets this, Alice will first verify if Bob can encrypt R2. If Bob can encrypt R2, then Alice trusts Bob. But Alice also needs to encrypt R1, so Bob can trust Alice. Okay, very simple protocol. However, this protocol doesn't work. Okay, we can easily do some, let's say, reflection attack or man in the middle attack. Let's say we have an attacker called Eve. if is pretending to be Alice. So if we're first send R2 to Bob, Bob will encrypt with the shared key between Alice and Bob and R2, and also send another challenge R1 to Eve. So the problem here is Eve doesn't have the key between Alice and Bob. So Eve will not be able to encrypt R1 using the key, right? So what Eve can do is Eve just create another session with Bob and telling Bob, hey, I'm Alice, and this is my random number R1. So Eve pretends this is a random number R1, but actually this is a random number generated by Bob in another different session. Then when Bob receives this message, what does Bob do? Bob will generate another random number R3 to Eve, and also will use the shared key between Alice and Bob to encrypt R1. Then after Eve got this number, Eve will go back to the previous session and send this number back to Bob. And Bob will believe Eve actually encrypted this message and believe Eve has the key, right? So you can see that this is called a reflection attack here. Alice was not involved here, but Eve proves she is Alice, right? So this is any questions so far for this reflection attack? Okay, let's move forward. So based on these attacks, people actually made some observations, come up with some lessons. So for two authenticating entities, we should not ask them to do exactly the same thing. So when they do exactly the same thing, we probably can use a reflection attack, right? And we want to use different keys for them, and we want to use different challenge numbers for them. And also the initiators, sometimes they are also more likely to be the bad guy. So the initiators should also be the first one to prove its own identity. Because those are the lessons we learned. Let's say if we want to do mutual authentication with a shared key, then what do? We'd say Alice and Bob share the key. Alice tell Bob I'm Alice, and this is my R2 random number. Then Bob will give another random number R1, and using their shared key to encrypt R2, go back to Alice. Alice will encrypt R1 and go to Bob. So this is the protocol we saw before, right? So if we, let's say this one, Alice R2. So those two are actually the same as previous one. So those are not secure ones. Okay. Okay. Let's skip this one. So you can see that. Yeah.
Sorry, I had a question. Sorry to interrupt. So is there no plan for when the private key is somehow compromised? So all SIM cards have to be changed.
You are talking about a specific the carrier example?
The 2G
example.
If the private key is compromised, then.
So in the 2G network, we are not using, so we are using symmetric key system, right? So if when you say the private key, I assume you are talking about a symmetric key, not really the public, yes. The private key part of the public key system.
Yes,
so
yes.
let's say if the authenticator, this part is compromised, then obviously all the SIM cards has to be replaced.
Okay, got it.
Yes, yeah, but this part is like the core network of carriers, right? It's well protected. It's harder to compromise that. Yeah.
Okay, thank you.
First of all, those let's say this server, they do not need to face the internet, right? The attack surface is much smaller.
So it's a completely closed off system.
It can be, yeah. They just somehow talk with the base station. There could be a dedicated wires lines to talk with the base station. Do not have to be internet. Yeah.
Okay, got it.
Yeah. So you can see that there are many possible attacks to crypto protocols verification like this, right? That's why sometimes when you look at the reflection attack, you say, oh, that's a smart idea to come up with this attack, right? But when the protocol becomes very complicated, it's also maybe difficult to find an effective attack. But at the same time, you also feel when the protocols are more complicated, there may be more holes, right? Kind of like software. When your software getting bigger, there may be more bugs you can attack. But how can we find those bugs automatically? How do we find the protocols problems automatically? That's why we use something approach called formal methods. So the Turing Award winner Leslie Lamport, he has some contributions to formal methods. I briefly talked about before. So in particular, there are some tools to formally verify crypto protocols, and the authentication protocols are a very important subcategory of crypto protocols. One of the tools I used in my research before is called ProVerif. As you can, the name suggests protocol verification, right? So it's developed by a team from France, I believe. This has been a very useful tool, and we used it to analyze a Fido protocol. So in this tool, how do we use it? Is we describe at a high level using ProVerif code what the attackers know, what the attackers can do. Then we define many different rules about the logic of the protocol. So basically, we code this protocol, we encode this protocol using this ProVerif language to describe how the protocol works. Okay, the crypto protocol works. Then we specify some data as or should be confidential. Then we can use the tool. The tool will try to find if there is a way to get the plain text of that data to compromise its confidentiality by using the rules of the protocol itself. If it can find a way to disclose the content of some data, it means the protocol has a bug. The protocol has some vulnerabilities, right? But like most formal methods, this approach may not be able to return a result. Sometimes it's just it will enter an infinite loop. It cannot find a result. So next, I will talk about a new protocol we are using. So actually, maybe many of you have been using this protocol. One of my contribution in recent year is to use ProVerif to verify this protocol, and we find some vulnerabilities of this protocol. So this protocol is called Fido. So how many of you heard of this before? Fast Identity Online. No one heard of this? So how many of you, when you when you use an app in your iPhone or Android phone, you are using the fingerprint authenticator. You use a fingerprint, then you log in your app, which like for the Bank of America. How many of you use that before? So I say at least one hands up there, right? Okay. So maybe two. Okay. So those apps actually are using this Fido protocol. So the goal of this Fido protocol is to, when you log in a remote server, they do not want you to give the remote server your text-based password. They want you to log in a real server, use a local and a trusted authenticator. In this case, the authenticator could be many different things. For example, the fingerprint reader on your phone, that could be an authenticator. So with Fido, the websites, the Reliance services, they do not need to store user-chosen secret anymore, at least after the original authentication, or even they do not need to store the hashes of your original password, which eliminates a major attack surface for e-business. For e-business, a major attack surface is your password or the hashes or password can be compromised. So ideally, the server side do not need to have any secret, but obviously the one we are using right now, still you have to start with the a text-based password. And also ideally your biometric information like your fingerprint doesn't have to go to the remote server. They never leave your own local device. So Fido has been supported by hundreds of companies, has been used in many different apps, and also there are some special authentication devices available based on the Fido protocol. So let's see how it works. Assume that you already have an account and password on a website. The first is you already register your account and password, okay? That's your old authentication approach. Now you want to register, you want to use the new Fido approach on the website. So you first start with registration, but here the registration is not to register your account and password. You are register your local authenticator actually. Okay. So you go to that website, you log in, then the website will send some message to your phone, and your phone should have some approved authenticator, like your fingerprint authenticator, which is a physical device on your phone, and that fingerprint authenticator is trusted by Fido. Okay, how do we trust that? When it is manufactured, it has some built-in keys. Okay, like public keys, private keys. So the remote server knows I trust this device. Whatever the device says, I believe that. Then it will generate some new authentication keys for your account, specifically for your account, and store those keys in that authenticator, not technically on your phone, but on the authenticator. Then there is a trust established between the website and your local authenticator. Okay, and the website knows that your local authenticator is somehow binding with your online identity. So when you log in, what happens is now when you log in, you are not sending your password to the website anymore. You first log in to your local authenticator, like you use your fingerprint, then your local authenticator will verify you by using those biometric information like fingerprints, right? So if your local authenticator verifies you, knows you are legit, then your local authenticator will do a challenge response protocol with the remote server. So the remote server in this point, it's not really verifying you. It's actually verifying your authenticator. Because it knows your authenticator is binded with your identity and it trusts the authenticator. If it can verify the authenticator, it also verifies your identity. Otherwise, you cannot log in the remote server. Okay, so that's basically how it works. So the key part here is the authenticator itself. It's certified, it's trusted. Fido certified many different authenticators. And originally, at the very beginning, the authenticators, when they are manufactured, they already have some trusted keys. We call them attestation keys. They could usually are RSA keys or other public keys. When the user logs in, first use the original password, then the authenticator will record your biometrics, generate new authentication keys for a particular website, sign the public key part of the new key with the attestation key, and send it to the website. So the website built the collection between the user's online profile with the authentication key. So after that, the real subsequent authentication is just a challenge response. But yeah, this is just another example. You can see here. This is another authenticator. This is a USB based. It's a fingerprint reader. Actually, you can plug this into your computer, then authenticate you. This device can authenticate you, and the remote server will just authenticate this device. Okay, this device is certified. The BOA example, the same thing. Many other apps has been using this as well. Of course, the local authentication part, there could be many different approaches. You can see the challenge response here is between the local authenticator and the server. And the local authenticator, how the local authenticator authenticates the user, the remote website doesn't really care, right? So there are many different approaches. You can use fingerprint, you can use face-based authentication, or you can also type a PIN or password, right? So that's just different stories. So we are basically changing one authentication to two steps, two authentications. So the protocol itself is quite complicated. Even the registration part looks like this. For example, this is what we had in our paper. This is a simplified version of the protocol. The protocol has more than 500 pages of document. We carefully read the protocol. We abstract the important parts of the protocol, and we summarize them in figures like this. For this is like the registration part of the protocol, the identities and what they do, right? For example, here you can say there's a random number S data, there's another random number challenge. So you can consider those as two challenge numbers for different purposes. Then those are sending to different identities. There is the user agent, so basically it's just the phone. Then there is a client, that's like the app. Then there is authenticator specific module, that's kind of like the driver. And then there is the physical authenticator, the trusted authenticator itself. So how eventually build the collection between the authenticator and the website. This is a complicated protocol, as you can see. But under the hood, it follows the challenge response paradigm. And this is the authentication part. You can say it's still very complicated. And some of the fields are even optional to support many different features. Okay. So what we did in this paper, in this project, is we read hundreds of pages of a document of the Fido protocol. The Fido actually has several, it's a suite of protocols. At the beginning, we analyzed something called the UAF, Unified Authentication what is UAF? I don't recall. Anyway, it's one protocol in the Fido. It's called UAF. So we read all the documents, 19 documents. We carefully abstract and formalized the protocol. We formalized the security assumptions of the protocol. We formalized the threat models of protocol. We formalized the protocol process and its own security goals. Then we code all of them using the ProVerif language, which is based on something called applied Pi calculus. So the code looks like something like this. Okay. Then ProVerif will verify a specific case, and then we automatically generated maybe 500,000 different cases, and we developed a tool we call it a UAF verif. And this tool will automatically generate different cases and feed ProVerif to verify if this is secure, if this is not secure. Okay, so in our lab we open source all our tools, so you can actually find this in my lab's website. The protocol process part, the code is actually only 900 lines of code. The ProVerif, the tool to generate that 500,000 or 400 scenarios is another 500 lines of code. Not many compared to our other program analysis projects we're doing in our lab. This is a very small project in terms of coding. Very interesting is when we do this project, we did find a bug of ProVerif when analyzing authentication goals. We reported that to the authors of ProVerif, and they fixed the bug in a later version. This is a project we did maybe two, three years ago. The paper was published like 1.5 years ago. Okay, we have a question here. Go ahead.
Professor, so the people who came up with Fido, right? So they wouldn't have used ProVerif for initially?
Very good question. So when Fido was designed, the community didn't do that. We believe in the future, when you come up with new protocols like this, you should always formally verify it.
Okay.
But before, people were not doing that. Yeah. And also things are much more complicated here, because so the spec, right? The official spec was only written in English. A lot of the things are very ambiguous, like the security goals they are trying to achieve. That's in natural language. Sometimes you cannot really understand what is the how do we formally define the security goal here. But all the formal tools, you have to formally define everything. Those were not those were not there when the protocol was first designed. Also, there are other people formalizing the 3G AKA protocols. It's authentication and key generation protocols, and they also find many bugs there, and they face similar challenges as we face, like ambiguous security goals, security properties, and assumptions. Yeah. Like I said, I believe in the future, when you propose a protocol, you should use formal methods. So we analyzed this, cost us like 80 hours, so not much. Yeah, very doable. So so here is like the verification results. We present them in this way. We present them in a way we call it minimum assumptions. So there are some security requirements for the protocol. The protocol says this data field should be secure. the confidentiality and integrity should be maintained. Otherwise, users' privacy may be disclosed, for example. Then we say to maintain the confidentiality of this data set, it means we need to assume those parts are secure. For example, this key has to be secure. This communication channel has to be secure. And we encode everything like this. For example, this one is like a private key of the authenticator. So obviously the confidentiality of this has to be maintained. To maintain that, it means in the case one authenticator, in the login step, those are the conditions, like the communication channel conditions has to be secure, whatever. For this kind of authenticator, no matter what you do, this one is secure, so it's okay. And for this kind of for this one, no matter what you do, it's not secure. Okay. For others, then there are different fields, like this is a counter. So the protocol may say, I want the counter to be confidential, so to protect user privacy. Then we say, if you want to do that, this has to be achieved. Otherwise, it cannot be secure. So that's basically our findings. Is everything is presented this way, and we summarized some interesting findings from tables like this. Obviously, tables like this only expert can read, right? So we summarized some findings. Like first of all, one of the access token mechanism in the protocol was not secure. Attackers can easily compute the token and impersonate a module there. And Fido did can prevent phishing attacks based on our analysis. Phishing attacks from malicious relying parties, from malicious user agent, and we find that Fido did meet the unlinkability property, which is related to the user privacy. Also, we find the registration the process has many bugs, more vulnerable than the authentication process. So that's basically what we find. The paper was published in NDSS, which is a top security conference. So in security, we have 4 big conferences: NDSS, Oakland, CCS, and Usenix Security. Actually, the reason I cannot deliver Monday's class is because I'm going to NDSS, which is in San Diego. Okay, any questions? That's all I have for today's class.
Professor, is there an alternate date for officers? You have those on Mondays usually.
So for office hours, you can just ping me on Slack. So usually I will ask you to try to schedule a meeting with the TA first. But if you want to meet me, then we can schedule a time. So right now I do not say, hey, the alternate day is Wednesday or something. I just want to have ad hoc meetings if you need. Yeah.
Okay, thanks.
Cool. Any other questions? Okay, if there's no other questions, I will upload the video later and see you guys next Wednesday. We will keep talking about authentication, then we move to access control models. Okay, see you. Thank you for being here.
Thank you, Professor.
Thank you, Professor.
Thank you.
Thank you.